Thank you very much. So first of all, I would like to thank all the speakers who made this workshop possible. I mean, they have provided a really great talk and shared their knowledge. Even for some, they shared non-published work, and that's really highly appreciated. I also would like to try to make a summary, but I open also a discussion for people who would like to discuss now, because we think we have a good grasp of the summary of all these nice talks. I don't think that all people has, because of this time difference, has like attended all the talks. But uh, in brief, if you would like to do high dynamic motion robots, or a new generation of robot that can perform high dynamics, from all the talks that has been presented, it's clear that the robot shouldn't fear going to contact with non-zero velocity speeds. It means that we need to be able, like we human do, contact without necessarily slowing down at the vicinity of the contact to establish the contact. Um, but if we can do that, it's because we have like important ingredients. The first one is, in my opinion, the hardware. So what pop up from all these talks, or from some of them, is that you cannot, of course, do high dynamic motion with robots that are not prepared physically, okay, to that. So I think that one of the important aspects of doing high dynamic motion is to have a robot which is intrinsically prepared in terms of mechanical ingenuity. But I like to say in one of the talks I have made that there is many people speak about artificial intelligence in terms of cognitive decisional aspect, etc. But for me, there is also the physical intelligence. I mean, the design intelligence and the AI. The intelligence should be also. It's not very much emphasized recently, but there are a lot of to do, okay, in the hardware to make the system, the robots first, like intelligent by hardware already. Then, from my understanding, there is also, if you have a robot that is really very well prepared for that, it's important to reconsider all aspects of the balance. I was really impressed by Dragomir's work. I think we do not see a lot, except of course Atlas. Many humanoid robots working with hands, okay, or working together with shaking like hands or dancing. It's very rare to see this, like robots that can perform high motion work together, having done or doing together very complex tasks. I appreciate also uh, the um, the fact that behind to achieve such kind of things, I mean, the control, you need a bit of deep control knowledge, like what Alessandro has presented, and also Roy at the end, but also a very good mastering of the there are things that the control cannot solve, and then you need to learn. Okay, thanks to what Odd has presented, it's clear that control formalism by its own now is not enough. Okay, to grasp all the complexity of the control and the planning that is required to do like such high dynamic motion. So we need a combination of both, and how this combination stands, what part of it is in the control, what part of it is the planning, is a very interesting aspect to investigate. So this is the global trend that goes out of all the talks that we have listened to. Now I want to give the stage to more the audience to ask questions on the fly for some presenters who are here or are still among us. So please don't feel free to speak and to say. One aspect also, which is extremely important, I forget that if you want to do control, if you want to do planning, the robot needs to be aware of itself. It needs to be aware of how he is evolving in this world. And then the talk of Mehdi has Ben Alek has also give good hints on how to handle these aspects of the estimation, which are of course very important because you cannot have sensors put everywhere for everything. And then it's good also to have to know how to combine the information or the data given by each sensor to take the whole benefit of it. So I would like really to give the stage of the speakers, even if they, because they might have listened to other talks and then they might have come by some comments or have new things to add. Please feel free. The stage is yours. Yes. I think which one you are, because I'm not the host, so you can see who are the people who are raising hands to give them
not yet.
to speak. I saw someone raising hand, so I don't know who.
Oh.
Or maybe it was just a mistake. So
maybe Abder, maybe yeah, maybe just to start a conversation somehow. Huh? So one of the things, unfortunately, about this situation is that ICRA, of course, is half in during the night, so I could attend only one part in the early morning here. So maybe I missed something, so it would be nice to get a bit of an overview here. So I fully agree, of course, that the hardware is essential. Huh? And my message is, okay, yeah, hardware is getting ready, but it's probably not at the same level of human bodies or animals, and there's constantly work there done to improve things. But can you perhaps summarize, if you were also there, maybe you what was the main message that you got there? Because there's more and more work done on different type of actuators. I've seen a talk also on flexible flexures. So also having this idea, if I have to do insertion, pick and place very fast, it's better to have flexibility here and there. And then I also hear about, yeah, there are vibrations, and all those things are there. And of course, our structure as a body, as humans, we have a really sort of a hard structure made by the skeleton, but then on top of it you have of course incredible structure, flexible structure that absorb vibrations, plus also the same time you have muscles that are capable of generating explosive forces and impacts that gives agility. So can you summarize, or you can summarize what what are the new trends there, if something was discussed about that? Or
yeah, I was since the start, of course, of the workshop. I think I can summarize to you, but then each one can add. There has been like 3 talks, or even a little bit, yeah, 3 talks. There was one which was more of a teaser, okay, on the actuation system. In fact, there is 3 categories of actuators. The one that you know, the electric actuators. There is pneumatics, of course, that hasn't really been said a lot. I remember when I was doing my PhD student, I had a team working on pneumatic actuators by doing hopping, really. Okay, because as you know, the air has a natural damping and many other known. It's surprising that I don't see, okay, this coming back. I don't know why exactly. I thought at that time, it was in the 90s, that they were having really, very good performances to make the robot jump and then even run with pneumatic actuators. Then there is, but this was not tackled or discussed. Even hydraulics was not really pop up. I mean, all the people are more moving toward the tendencies using actuators, electric actuators. So then, for me, there is a lot of aspects of discussing whether you do torque control or position control, and position control is high stick gains. But for me, it was always the problem for me is whether your system is reversible or not. Okay, it's backtrackable. Okay, in French we say reversible, but the correct English is factorable. So if I sum up, I mean, two of the talks has sum up nicely that there is electric actuators with G ratios that harmonic drives, etc. There are others who do like who add variable elastic actuators, variable stiffness elastic actuators, all these SLAs, which is in fact exactly the same, but you have a stiffness at the at the end of the linking the output of the shaft to your link, I mean to the body of the robot. And you have, for me, it's the inheritance of telerobotics, of teleoperation, the same actuator that you use for haptic feedback, for instance. They call it high torque actuator. It's what Kim Sang-bai has made and others has tried to replicate. But for me, these are good if you, I mean, I don't see how you can do that for bipedal robotics, for humanoids, let's say, because it's good for legs that are nearly not holding a lot of mass, like the sticks that you use in haptics, etc. So it's more suitable for multi-legged robot like quadruped, etc. But of course, I mean, if you have a back drivable robot, and you can, of course, absorb more impact. Okay. There is other thing that was surprisingly missing, and then I will jump up to your remark, is, for instance, the fact that all human beings, we we have like, we are kind of endoskeleton systems, okay? It means that we have a rigid structure or surrounded by inner bag, which is our muscles and all what comes after. In robotics, is the reverse. It's all the structures outside where the robot contact in the body, they are rigid. Okay, and you're right. Then there is nothing really which absorb all the energy that is occurring. Okay, at the impact. It's very interesting to see why, for instance, the robotics community is going more further toward having these rigid covers and shells instead of thinking to have something which is more of a more flexible or damping carapace or a shell for the robot system. That's also a solution that could be studied, but I didn't see a lot of work going on this direction. And this is basically what get out of the discussions from the hardware point of view. Then, of course, each talk has sophisticated the design for trying to optimize, of course, the design with the task that you want to do so that you consume less energy, so that you use or you exploit the impact to store energy, to restitute it after. So it's, I think, things that are classically well known, let's say.
Thank you.
So each one, I don't know, and other people, please feel up to.
I think there is a question in it.
Oh yes, there is someone raising hand. So Riza, if you want to, could you please
yes,
ask your
thank
question?
you.
Yes.
I'm Reza Qapçılı from Tampere University, Finland. Nice to see you, Alex. Long time no see. So unfortunately, I missed most of the presentation, but just comment about this, the last discussion regarding the hardware, especially hydraulics and pneumatics. That's the research we do with big machines, especially that you see some of them behind me in our lab. Main thing with hydraulics and pneumatics is that they are not efficient in terms of energy. So if you have a mobile platform, if you have a machine like that, I have a diesel engine, it's fine. But when it's electric and small kind of walking humanoid, then it's a very different thing. The efficiency is very low. Of course, there are a lot of activities we do to increase the efficiency. That's one thing. The second thing is that they are difficult to control, so it's compared to electrical drives. So that's why probably most of the researchers have moved toward electric. They are much cleaner. Electric is much more cleaner. It's easy to set up. You can just even nowadays buy, because of all this electric movement, bicycle, etc. You can even set up your own build, probably your own system. But the problem with electric is that they don't have a zero speed torque, and that makes them difficult, and they're not very good for, I would say, not for human actually, because for human you need very high accelerations in small speed. Hydraulic is good for that, but they are not efficient in. They are I don't know actually the field exactly, but I just that was my input to this discussion. Thank you.
Thank you, Reza. Very nice, very valuable points. Actually, I fully agree with the point that the electric motors cannot provide the zero speed torque. So basically, our humanoid robot it's not good for our humanoid robot to stand for a long time without moving. Yes. I think Abder remind me several times for these issues. So thank you, Reza, again very much.
Yes. For the hydraulics also, for to get those, typically they have a dead zones. It makes it also difficult to control around zero speed, but they can just stand without energy. So this is a good thing. Some good combination of those could be useful. And of course this high power Boston Dynamics robot, they're all hydraulics, but they have their own specialized design, and I don't know how efficient they are, but I haven't really studied in details, or probably they are not even available.
Oh, yes.
Thank you.
Thank you. By the way, Reza, have you ever applied the quadratic optimization-based controller on the hydraulic machines in your department?
We do, of course, MPC, yes. Quadratic optimization, we typically do for trajectory optimization, not for control.
Ah, okay. Okay, good.
Yes.
Is there like more remarks on the hardware side, or can we like jump into the control? And then I would probably ask Aude, because she started now to work with like the team, who is known to be a tough guy in control, and with Alessandro now, who is starting to, there is this combination of like control and learning. What's your opinion in how, in both approaches? I mean, do you see Alessandro, like I'm seeing now that there are some things in the control that need to be really tackled partly by machine learning techniques, and that how would it, in your opinion, be more easy than to provide strong proofs like all is doing now? So how do you see this interplay between machine learning and like classical model-based control, let's say? Let's say machine learning control and model-based control.
No, I think it's of course also classical control model-based. Also, if you come from the control field, yeah, identifying models from data has always been there. And if you go also in the area where I am currently in the Netherlands, yeah, you do the control of most of the machine, high performance, acceleration of 10 Gs, and all of these models are based on data. They don't even try to model them without looking at the data. So what is now emerging, of course, is also that you can learn the kinematics of a robot with just measuring, instead of trying to use length and information. Also the dynamics, and Aude was talking about that. You have a flying object, you can use data, and then you try to get models, and it's probably too difficult to come up with these models. And I think that also for impacts, yeah, at a certain point you could do a lot of experiments, or even in simulation, to try to get a good approximation, at least statistically, of what happens if you have an impact between the robot and the environment. And I think these things can be learned. So I think that there could be quite a lot of work done in trying to learn also this impact map from real experiments. And when these are learned, these are sort of memories for a robot, and then they probably can be used to reason. In the same way we use models for free motion and contact motion. At least this is my my view at the moment.
So when we speak about impact, we also speak about having rich models that account for, how to say, to reflect really the vibrations that are occurring and then the impact, the contact clues for unilateral contact. I have a question to Roy. So because he's obviously worldwide known by everybody, like in robotics, he's using his algorithms for computing the dynamics. And so, Roy, do you think that there is a chance that we could have that we could scale this these models to reflect how the impact is propagated inside the structure, and to be as accurate in how to for instance, to replicate very reliably like the dynamic of a robotic system when after the impact by integrating like some flexibility in the joints and being able to compute the whole dynamics of all this. So what do you think? So do you think that's not necessary? Do you think it's that you have tried already, but it's not easy, or that the algorithm doesn't scale well? So I would like really to have your opinion on that.
Well, in my opinion, impact dynamics is an area where the rigid body assumption doesn't work so well. And you're better off treating impacts as compliant contact events rather than rigid impacts. If you do this, then you have a chance to get the timing right. This is one of the big problems with impact in a multi-rigid body system. The outcome depends on the assumptions that you make about the ordering of the ordering in time of the impact events. But if you assume instead that the impacts are compliant contacts, then they don't happen at a single instant, they happen over a period of time, and then the simulator or the dynamics calculation algorithm can get this aspect right. It can figure out the flow of shock, let's say, mechanical shock through the system. I think this is something that you can do at least approximately, but I'm not convinced that it's a good long-term strategy. I think if you pursue this, you're making the mistake of looking on too short a time scale. These things happen in tenths or hundredths of a second, yet humans and animals achieve very much higher performance than robots, despite the fact their reaction times are 10 to 100 times longer than these impact events. So nature tells us you don't have to respond on a millisecond by millisecond timescale to external and internal events. It's okay to be a bit slower. So that's my opinion. It can be done, but I'm not convinced that it's a good idea.
The point of having like to model just the compliance at the contact level, in my opinion, will not be enough to reflect the how the energy travels inside the structure, especially if, for instance, people to do high impacts, they tend to have really compliant joints in a way or the other by using like stiffness or by even sometimes by control, having low gains, as you in one of your video you have showed it. So do you think this? I mean that there is no need to model that the compliances in the structure so that they could reflect really how the impact is propagated inside the structure?
Well, the big problem here is that You need an accurate model, otherwise the simulator's predictions won't be any use. And the more detail you put into the model, the more you have to measure accurately the behavior of the component parts. How flexible is a link? How much compliance is there in a joint bearing? You need to measure these things before you can put the data in the model. And let's remember that some of these things are non-linear. For example, springs. If you have springs in the robot, there is typically a certain amount of internal friction in the material of the spring. So you have a hysteresis effect. And if you're not prepared to model hysteresis in your simulator, which is not easy to do, then that's a significant dynamic effect that you're choosing to ignore. So I repeat, I think it can be done, but I'm not sure it's a good idea because of the sheer amount of detail that's needed before the model will really give you accurate predictions.
Okay, thank you very much. Thanks for this.
Abder, can I comment on this, because I would like to hear also Roy's view on this. I fully agree that thanks, Abder. I fully agree with Roy that try to get an accurate model is really difficult. So you start from rigid body dynamics, you start maybe adding flexibility on the joints, maybe even on the links. And this is probably a very painful process to get the model right. What we observe, and at least the way that I'm also thinking of these problems now, is that fully rigid robot model with impacts are still okay to grasp the main trend. So if I take, for example, a KUKA arm and I'm smashing on a table, and this is actually what we started doing a few years ago, and then you take the model of a KUKA and just a fully rigid model, and you equip with a simplified impact law, really say, like, okay, there's an inelastic impact in the normal direction, and then you look at the result of doing the simulation and looking at the real experiments, you see that, yeah, the full rigid model with the simplified impact, of course, doesn't show any oscillations. It's just jump in the velocity. You do the real experiment, you see a jump in you don't really see a jump in the velocity, you just see that the velocity spikes up and they start oscillating about 100 milliseconds, and then this oscillation goes away because, yeah, it's damped by either the low-level joint torque controller or the structure. But what is interesting is that there is the fully rigid model, and with the simplified impact law, is still able to capture, yeah, the gross jump in the velocity. So, yeah, my suggestion, or at least the things that I'm trying to explore, is that, okay, can we still calibrate this simplified impact model even with real experiments? Yeah, not hoping to be able to reproduce the oscillations, but at least to get this model calibrated, so at least we know that the velocity of the robot, the real robot, will jump about a certain point in the state space, and then of course you have to be prepared that there will be oscillation in that region, and you probably don't have to be too aggressive in trying to react to those. So probably you want to have low gains just after an impact, but at least you are prepared to have a trajectory or a reference that is nearby where the system really jumped to after the impact. So I would like to hear from Roy if he experienced or have any opinion on this.
Well, it's certainly the case that rigid body models will give you something interesting to think about, and that they do capture a large amount of the real behavior. My earlier comment was specifically about impacts, collisions. For general continuous motion, rigid body models, the rigid body assumption is mostly valid and useful. It's just these short events that happen with collisions where the model is less useful. but you're starting to move in an interesting direction here, because there are systems where details are really important, and there are systems where details don't matter so much. And if we think of the system as being the robot, its environment, and its controller, sometimes we get incredible success. Think of Raybert's original hopping machines. They were an amazing advance on previous works. These are systems which, by their very nature, little details don't matter. If one hop isn't quite right, so what? Nothing serious happens. But there are other systems, like robots, are early attempts to implement hybrid motion force control, where as soon as the robot touches some object, it begins to chatter. And this is a system where details matter because they affect the objectives of the performance. And maybe what we should be trying to do is find out how to design a controller so that the complete system is agnostic to these little details in the dynamic behavior of the environment and the robot.
Oh, I have a comment on this.
A very quick answer to Roy, and then if I can, and then I'm very interested to start the conversation. So I fully agree on neglecting certain aspects, and I also think that indeed, and I think this is related to also what Roy was saying, you also need to have the right hardware. I don't think we have a metal. You should care about controlling metal robots impacting metal structure, and in that case, also all this rigid body assumption won't give you a good prediction because the order of impacts will matter. But I think there are particular type of impacts for which prediction are possible, and for which probably also impacts is providing the stability. So you don't have to care about the stability because the impact dynamics is providing that. And I think this is the case also when we manipulate objects. That's why maybe we are so successful. And this is the only comment that I wanted to make.
Okay, so I have done some work on free-floating space robots, and also on robots mounted on a flexible base. And definitely impacts, rigid body model for impact has one merit. We can use it for post-impact control, because you can get some, you can solve the equation and you get the step in the joint velocities, and that helps to plan your post-impact control. And we use this for very fast suppression of the vibration. So vibration suppression, it works very nice. So at least at this aspect, you can use it very nice, I think.
Thank you very much. I will be very interested in looking at your work on this.
So we can now talk a little bit more of control and balance, because that's also one of the important aspects that we have mentioned. I was also much impressed by Kanamiya Sensei's work. So I was wondering if I compare, for instance, because you have made like this human monitoring system, human capture system, and I really like the fact that you put the person like on a sliding and try to keep do the motion without really sliding. It's really interesting. But then when I saw the videos, I was wondering, why do we have like, do you think there is any way so that by using momentum control, we end up by algorithms to have motions that are less jerky? Because the robot in the simulation, you show the robot has the tendency to do like high acceleration at the start. But when you look how the human are balancing, even in high dynamical motion, they tend to have really low frequency motion to balance, basically. Even if we take advantage of momentum strategies in the way we balance generally, so we don't generate necessarily high accelerations to balance, except of course in these particular cases where we are needed to fall and then we do this quick stuff. But in most of the cases, even sometimes for the pushing, I used to say that for humanoids, this compliance is important, okay, because it stabilizes, okay, the walking, but it makes the control complicated. It's like you have an antagonistic property where being compliant is nice, okay, that helps the balance, basically, it helps the strategy of the balance, but on the other hand, it makes also the system much more difficult to control. So what's your opinion on this, and how's your future perspective on trying this on real platforms? Ours are open to you, as I told you some months ago. Yeah.
And thank you. For, yes, actually, I had one example, and that is this long jump, standing long jump. When you aim at perfect motion, so you can make this perfect motion, and but you need very high accelerations for this. And as you mentioned, yes, really humans do not this. So therefore, I included also the this long jump performance, our modeling of perfect one with high acceleration, and another one where the robot lands first with heel strike, and then in order to damp out the angular momentum, it has to make a toe rotation. And this was like a non-professional jumper. So professional jumpers, they can land very nicely without toe rotation. So, and this we found out we could model it because there is a basic fact that the central nervous system, it takes about 200 milliseconds, about 100 or 200 milliseconds, there is a time delay. So this is how we model this, and we got this toe rotation. And I think this is one important direction in study, because it's not always perfect. It's like you mentioned. So this gives you a little bit not so high accelerations. So you have some time, but it's of this order. So 200, 300 milliseconds, and it's important to go into these details, I think. I don't know if this answered your question.
Okay. Yeah, of course. So is there any other concern for the control aspects that you would like to raise or discuss? I saw that Aude has left, that's why I didn't jump up on her again for her opinion on the interplay between like learning and the control. So, but now if you have any aspects that you would like to raise on the control or any other question. I don't know if Mehdi is still here among us or not, because then he could also, I would be very curious to know if all the approaches that he has developed for estimation of the states of the robot could apply at a very high frequency. And the impact, I see that he's still here, but I'm not sure whether he can speak or not.
Yes, I'm still here.
Okay.
So yeah, for now the frequency of so you're looking for the frequency of the impact. I mean, frequency of the detection of the impact. If I'm not wrong.
Yes, it's this, because the frequency of detection of the impact, and also you know that after the impact, if your robot is moving, everything will jump up. It means it became non-smooth. So I was wondering how much because the system that you presented for the observer, I'm not sure how they behave if there is a jump in the state that is due to impact, for instance, during the motion. And
Yes.
just to have a hint, because I'm sure that we can discuss about it more in detail, but I was curious to know whether you have thought about it, or whether you have like an idea of what will happen if there is a jump and a sudden jump in the state, which makes it non-derivable, basically.
So I have presented two solutions. One which tries to estimate the impact or external forces, and the other one that estimates the state of the robot in a way that is independent from the motion itself. So for the first one, I think it would not be able to quickly detect an impact. It's based on Kalman filtering, so it would be it would lag. It wouldn't react immediately. It would converge eventually, but it would not be good for quick detection. But in the case of the second one doesn't detect the impact. Maybe you can kind of build an impact detection based on it. But the second one is able to completely reject the impact. So if the change of state is visible in the gyroscope, it would be immediately taken into account because it's based on complementary filtering, which is known to have no delay, no phase shift. So it would immediately correct the state without a problem. The issue would be if the assumptions that we make are wrong. For example, if the impact is so strong that the robot is jumping in the air, that would, of course, would not follow. So maybe it was my presentation was a bit early, so maybe not everybody has attended. So the assumption I was making for that estimator is that we know the coordinates in the robot frame of a fixed point, a point that has zero velocity at each instant. The fixed point doesn't need to be fixed. I mean, it doesn't need to be constant value, so we can update the position of the fixed point. But this can be, for example, for the case of humanoid robots, this can be the ZMP, which is a point that we know is in contact with the environment. That's more or less a fixed point. If this assumption is still correct, we can, the theoretical development of the estimator is able to immediately take into account any motion.
So what is your,
sorry?
What, because I didn't hear about this, I didn't hear you speaking about the approaches, the comparison with the approaches that are using residuals. I mean, those developed by Eichstricht and at the Lucas lab. How do you compare with them? I mean,
so that's mostly the first method, and it's kind of complementary because my method doesn't use at all the torque measurement.
That's true.
So if you have also torque measurements, it means that you have like two different measurements of the same thing. You can definitely use the redundancy. So
but
yeah,
your robot is torque control. Why you don't have torque measurements?
In the estimator of the robot doesn't have to be torque controlled. And even when I use torque control on my robot, I don't have the torque measurement. I have only the feed forward. It means the torque that is sent by the motor, which then is added to the friction and added to any elasticity or anything that happens afterwards. So we don't have the torque feedback. So that's why we have in the control loop we have integral terms to compensate for the difference between the feed forward and the actual motion.
Okay. So is there anything you would like to talk or discuss? Do you think we have covered most of the open questions? If so, maybe, sorry?
Yeah. It was really important, I think, that the hardware has been addressed. That's, I think, something that's really good in this workshop. Yeah, the presentation of Patrick Van Sigma was also really nice with that regard. So I hope that people who missed that could be able to catch up. I think it's still available in the stream.
It's recorded. everything is recorded, so people can, of course, go through these presentations again, and then get of course to contact the presenters if you have further questions.
Yeah. So I agree also that back drivability is something that's really important, as you said. In our robots, it has like really low back drivability. So when we try to do like compliance, if you saw the video, like the zero torque sent by the motor is still really hard to move, because the arms of HRP5P are so strong that it can lift the robot itself. So it has like really high gear ratio. And this has been a problem for us because it means we have high frictions and we need to compensate for them. So I think that design can be really changing a lot for the control of or impact aware control of robots.
But you see, for instance, the HRP5 is really a good example that allows me to jump up again on this problem of, you know, when it walks, it shakes a little bit. When it does some tasks, I saw that it shakes a little bit. So, and we do have we don't, because we don't, first of all, our controller assume it's a rigid body and the rigid articulation, but in practice, I think there is a way that you could actively suppress these vibrations, okay, if we know how to. We have in our team Aziz, who worked a lot on stabilizing flexible joints and flexible even links. And I know there is a bunch of work in control to do this actively, okay, to really make the robot walk very smoothly. And the more they are heavy and bulky, the more, of course, the impact propagates in the structure and makes it vibrate. Whatever sophisticated mechanics you use inside, you have to deal with the weight, so that you use materials that are necessarily not does not have high mass density, and then obviously if you don't have a high mass density to reduce the weight, then you create flexibility, and then you need to deal with them. We do have them as well, but we don't vibrate when we work.
Yeah, so we have the you know, the curse of this square law. If you make a robot that's twice bigger, it's 8 times heavier. Yes. But the sections are only 4 times bigger, the sections of the joints. So it means that the pressure is much higher on the bigger robot and than on the smaller robot. So any flexibility.
In biology, people call this allometry. In biology, this is the reason why in the nature you cannot find living species, terrestrial living species, that have exoskeletons bigger than the crab. And if you could have, like the coconut crab, and you cannot find on Earth a living species that has a rigid exoskeleton bigger than the coconut crab. And the reason for that is that they couldn't survive. Okay, the nature would just, the impact would kill them basically, and they couldn't find any way to survive and to be safe in the nature, in the wild.
They have also the problem of breathing. They breathe through their
yes, absolutely.
Shell.
So there are many aspects,
but
but you don't have in the nature more than a coconut. But in robots, you have like big, huge robots with like very rigid shells, and this definitely is a counter nature already. And this is the reason why I was saying later on that in the robotics field, we have to change a little bit our mentality if you want to go into high dynamic motions. We have to rethink the way we do robotics, in my opinion.
Definitely.
I don't have much to ask and say, so if you guys want to talk further, I'm very happy to stay, and if you want to raise any other issues. So as I said, the stage is yours. If we think that we have covered mostly everything, and because of our Asian colleagues, I think it's too late already for them. It's probably 8 p.m. now, or 9, I am not sure. So I will give back the stage to each one to close up the workshop. And thank you all. If, of course, still you have time if you want to raise any other issues. If not, so maybe which one you can close the workshop.
Yes, thank you, Abdar. Thank you very much for joining us from 3 a.m. It has been very, very difficult
Well,
for
you
you.
were there as well. You are impressed. It's okay.
Okay. Yes.
As most guys, it wouldn't be fair not to be there, right? So that's something you need to give the example.
Yeah.
I wouldn't be sleeping, and our colleagues are sleep. We are sleeping, and the colleagues are speaking. So it's not good.
Yes. Okay. And then I would also use this opportunity to thank the Chinese team again, co-share team again. They are still supporting us on the live stream. I think we had, in summary, we had a wonderful workshop. We have went through so many interesting aspects. Hardware controller co-designed by many presenters, Patrick Wensing and the others, and also the momentum-based control by Najib and Roy Featherstone. And we also covered software materials and even the learning approaches. So hopefully everyone can find his or her own pearls in this workshop. And I will collect all the records and put them up on the workshop website. And according to ICRA's requirements, they are going to be there for at least 6 months. And after that, some of the presenters require to remove their presentations. So I will leave the choice to them. If there are no remarks or or questions, as Abder said, it is already late for our Asian colleagues. So maybe let's close here. Hopefully, after the pandemic, we can meet each other again physically and exchange ideas more effectively. Thank you all for being with us.
Thank you.
Thank you.
Thank you. Thank you very much.
Thank you. Bye-bye. Thank you, Alex.
Thank you. Bye-bye. Great.
Thank you. Thank you so much.
I forget to say hi to Alex. Sorry.
Hi, Esther.
Hi, Alex. How are you doing?
Good. How are you?
I didn't recognize you. I mean, you are getting younger each time. So that's
Really? Okay.
Yeah, you have to give me how you do that. You have to tell me what is your secret.
It's working.
You're like a teenager. Come on, I mean, what are you doing?
Actually, yeah, I'm not in the manipulation direction yet. Just I'm working on marine robotics and service robotics, and put an arm on a ship might be interesting. So
yeah, I
thanks,
saw a talk of one of your colleagues, right?
Yeah.
Is it in your lab this talk with the robot who were balancing the arm but trying to grasp this
yes
the drone?
Yeah,
it's in your lab, right?
Yeah. Actually, you might not be able to balance too much using traditional ways. We are thinking about whether it looks like a Chinese Tai Chi, and so that you utilize the vibration to catch at appropriate areas.
Okay.
Yeah.
So we need to do that with the humanoid robot. We put humanoid robot on the balancing and then try to grasp UAV. So like a human, you know? You have like a unilateral contact on a balance, and then you.
Yeah, there might be some. These are compact. Yeah.
It will make it more complex. Yeah.
Yes. Now we are putting the arms onto a ship, onto a USD at this moment, and if there are more outcomes, I'll let you know. Wow,
it's an amazing work. It's really. I was really much impressed, by this robot and trying to grasp this UAV. Impressive.
Yeah, hopefully.
How are you doing? How is the situation in China now?
Now it's good. But in Shenzhen, we kind of recently there be about 10 cases, so it's also getting much more nervous.
10 cases. Come on. I mean, cases. If there were 10 cases in France, people would do the would be like dancing on the streets and everywhere. Here it's still like a bit serious. Yeah. It's getting down, but slowly, not as fast as we wish.
Yeah, it's getting down. Yeah, hope you take care.
Yeah, of course, I will try to do our best. Yeah. Okay, so thank you very much for helping and for assisting each one, for doing all this and for your contribution and for everything else. I really I still remember your hospitality in Shenzhen and the good food we had and everything. So
Yeah,
I'm eager to travel again to China. Yeah.
Yeah, it's a wonderful workshop. Congratulations.
Yeah, thank you very much. Yeah, thanks. It's huge ones who did everything. I did nothing basically.
Except from joining from 3 a.m.
Yeah, except joining coffee. Yeah. Good. So thank you very much and goodbye. Bye bye.
Bye-bye.
Thank you. Bye-bye.